Hello students, myself Dr. Divya Ghildial in continuation with my lecture series on relativistic mechanics as per AKTU syllabus for BTech first year students. I have already briefed you about Galilean transformation equation, Lorentz transformation equations, length contraction and time dilation. Now I will tell you about relativistic velocity addition theorem. As you can see, it has been asked and it comes as a 10-mark question. State and prove the velocity addition theorem. Show that the theorem is consistent with Einstein's second postulate. Okay. First, we will draw a diagram. This is my two frames of reference which I have taken, in which frame S dash is traveling with velocity v and frame S has been taken as the inertial frame. Now we will take the velocity components in all three directions, that is ux, uy, uz for the frames S and S dash. Also, from our basic concepts of mechanics, we know that velocity is rate of change of displacement. That is, u is equal to dx by dt. So here ux becomes equal to dx by dt, ux dash becomes equal to dx dash by dt dash. Now, from Lorentz transformation equations, either in the inverse frame, we know that x is equal to x dash plus vt dash upon under root 1 minus v square by c square, and time t is equal to t dash plus x dash v by c square under root 1 minus v square by c square. What we will do is we will differentiate this x value and this t value independently, and then we will divide them to get the value of velocity, dx by dt. Here we divide and we get this expression. We simplify it more further and put ux equal to dx by dt, and we get ux is equal to ux dash plus v upon 1 plus ux dash v by c square. Similar expression will be obtained for y and z frame. Similarly, for an observer in frame S dash, velocity components can be written by using Lorentz transformation equations with the negative sign. Now, what next is important in this topic is that show its consistency with Einstein's velocity of light relationship. That is second postulate. Let particle be moving with velocity c in frame S dash and is also moving with velocity c in frame S. That means in both the frames it is moving with velocity of light. So in this equation, ux dash is also c, v is also c. You put cc. What does this reduce to? U reduces to c plus c upon 1 plus c square by c square, which is equal to c. So this expression is valid, and it is proving once again the second postulate of Einstein, which states that velocity of light is same and it is a universal constant. Second, if a light signal is traveling at a velocity v in a stationary frame S dash, then its velocity is estimated by an observer in frame S will also be c. U y dash is equal to c and v is equal to 0 for the stationary frame. Again, we will return back to it being equal to velocity of light. Two particles come towards each other with the speed of 0.9 c with respect to the laboratory. What is their relative speed? Right now only we have derived the expression ux dash is equal to ux dash plus v under root 1 plus u dash vx dash upon c square. We have been given Vx is equal to 0.9 c and V is also equal to 0.9 c. Putting these values in the above expression, we get the answer. We can take one more numerical on this. An experimenter observes a radioactive atom moving with a velocity of 0.25 c. The atom then emits a beta particle with a velocity of 0.9 c relative to the atom in the direction of its motion. What is the velocity of beta particle as observed by the experimenter? So from the numerical, we know that we have to apply the law of addition of relativistic velocities. U is equal to U dash plus V upon 1 plus U dash V by C square. U has been given to us as 0.9 C. V has been given as 0.25 c. We put these mathematical values here. C is velocity of light. We do not need to put the numerical value because automatically C will get either cancelled and we will be left with 0.9 for C. Next, relativistic variation of mass with velocity. Till date, we had this expression in mind that mass is a universal constant and it does not vary. But Einstein proved that rest mass is constant, but the relativistic mass can also vary. In order to derive the expression m equal to m naught upon under root 1 minus v square by c square, we will be using the principle of conservation of momentum before and after collision. So for this, once again, we take a frame of reference S and S dash. We take two particles of masses m dash and m, velocities u dash and u moving towards each other. And this frame S dash is moving with velocity v. Now we make these particles collide. So from law of conservation of momentum, momentum before collision should be equal to momentum after collision. For elastic and inelastic, two cases are there. We in this case are going to take where the masses add up after collision. So that m1 u1 plus m2 u2 is equal to m1 plus m2 into v. Also from relativistic variation of velocity, we know that ux is equal to ux dash plus v upon 1 plus ux dash v by c square. Now since one mass is moving in this direction and the other is in the opposite direction, so if I choose one direction as positive, then automatically the opposite will become negative and we get u1 is equal to u plus v upon 1 plus uv by c square. u2 dash is equal to minus u plus v upon 1 minus uv by c square. See, here is u is positive and this u is negative. Now we will put these values of u1 and u2 in this expression, which is showing the law of conservation of momentum. After putting the values, we will divide this whole expression by m2 so that it becomes more simple. And then here m1 by m2 becomes equal to 1 plus uv by c square divided by 1 minus uv by c square. What we will do is, now we are going to use the squared form of velocities u1 and u2, which we get from here. u1 and u2, relativistic addition of velocities, 1 minus u1 square by c square is equal to 1 minus 1 upon c square. u1 is u plus v upon 1 plus uv by c square from the relativistic addition of velocity. Solving this expression further, we get 1 minus u1 square by c square is equal to 1 minus u square by c square into 1 minus v square by c square divided by 1 plus uv by c square's whole square. Similarly, for u2, we get the same expression. Now, we will divide u1 and u2 values and we get the expression as 1 plus uv by c square whole square upon 1 minus uv by c square whole square. Now, what we will do is we will take square root of this expression and put this value in equation 3 here, and we get m1 upon m2 is equal to under root 1 minus u2 square by c square upon 1 minus u1 square by c square. If a body is at rest or is moving with zero velocity in stationary frame S, then u2 becomes 0 before collision, and if m2 is equal to m0, the rest mass of the body becomes m1 is equal to m0 upon under root 1 minus u1 square by c square. Commonly used notation, we can write m is equal to m0 upon under root 1 minus v square by c square. This is the relativistic formula for variation of mass with velocity. Now, from this, we can once again conclude that this will be valid only till the time v is approximately equal to c. It will not be valid if v is very much less than c and if v is greater than c. As the velocity of body in relative to the observer increases, the mass of body increases. When v is very much less than c, then the mass reduces to rest mass. Relativistic momentum and force, we now know that m is equal to m0 upon under root 1 minus v square by c square. We know from classical mechanics that momentum is equal to mass into velocity. Now, instead of m, we will write m0 upon under root 1 minus v square by c square. So we get p is equal to m0 v upon under root 1 minus v square by c square. Force from Newton's law is defined as rate of change of momentum. Hence, F is equal to dp by dt, or P is mass into velocity, so it becomes equal to d by dt of m naught v upon under root 1 minus v square by c square. Now, this is very easy. Just remember, wherever classical physics gave m, instead of that, for relativistic, put m as m0 upon under root 1 minus v square by c square. Then you will easily derive the formula for force. You will easily derive the formula for momentum. Let us have a look at the numerical that is asked from this portion. At what speed will the mass of a body be 2.25 times its rest mass? From my concept of mass, we know that m is equal to m0 upon under root 1 minus v square by c square. We have been given that m is equal to 2.25 m0. So instead of m, I will write 2.25 m0 is equal to m0 upon under root 1 minus v square by c square. This m0 and this m0 will get cancelled and simply cross multiply to get the value of v. A man weighs 50 kg on the earth. When he is in rocket ship in flight, his mass is 50.5 kg as measured by an observer on earth. what is the speed of the rocket? We know from relativistic variation of mass with velocity that m is equal to m naught upon under root 1 minus v square by c square. We have been given m as 50 kg on earth. That is, sorry, his rest mass. So this becomes m naught, and m is 50.5 kg. So we put the values here in this expression and we get the answer for velocity. So there are many more questions. You can refer my notes for it. Mass energy equivalence, Einstein's mass energy relation. From Newton's second law, we know that force is equal to rate of change of momentum, and also momentum is mass into velocity. Work is force into displacement. So it is equal to, instead of F, put dp by dt into x. So work becomes equal to dp into v. Also, we will now differentiate this value. So we will use the concept of differential formula for two multipliers. The differential formula is that first one quantity stays constant, you write differential for the other. Then second time the second quantity is constant and you write differential of the other quantity. So we differentiate this equation. dw is equal to v square dm plus mv dv. Now instead of m, we will write m naught, we will write m equal to m naught upon under root 1 minus v square by c square. Or a simple trick is cross multiply and square the value. So you get this equation, m square c square minus m square v square is equal to m naught square c square. Now we will differentiate this equation once again, and we, after differentiating, we get v square dm is equal to dm into c square minus mv dv. This value we will put in the expression for work above here. dw is equal to v square dm plus mv dv. Very simple. And we get dw is equal to c square dm, because from work energy theorem, work done in displacing a particle is the kinetic energy that is given to the particle. And we also, you can integrate it to find an expression for kinetic energy, which is equal to m minus m naught whole into c square, and m naught c square is the rest mass energy. So this is the universal mass energy equivalence. If v is very much less than c, then this kinetic energy expression also gets converted back to non-relativistic mechanics. This, instead of m, now put m naught upon under root 1 minus v square by c square, and you observe that if v is less than c, it will get back to k equal to half m naught v square. That is kinetic energy of classical physics. You can also derive one more expression showing the relationship between energy and momentum. Let us quickly do a numerical. The mass of a moving electron is 11 times its rest mass. Calculate its kinetic energy and momentum. From the work energy concept, we know that K is equal to M minus M naught into C square. We have been given M equal to 11 times M naught, and M naught, that is rest mass of electron, is 9.1 into 10 to the power of minus 31 kg. At times in the question paper, if the constants are not given, then please apply them on your own, or you leave the answer in terms of constants. So we put this value here in this expression and we get the answer. So quickly, let us revise relativistic mechanics. What did we study in relativistic mechanics? We studied that Galilean transformation equation, that is x dash equal to x minus vt failed, Lorentz did an addition in this expression and wrote that x dash is equal to x minus vt upon under root 1 minus v square by c square. Then in relativistic mechanics, we studied that time length contraction L naught is equal to L upon under root 1 minus v square by c square. Time dilation is equal to del t upon under root 1 minus v square by c square. Rest mass or variation of mass with velocity m is equal to m naught upon under root 1 minus v square by c square. Relativistic addition of velocities, ux is equal to u plus vx by c square upon 1 plus uxv by c square. This is when we consider the addition of velocities for bodies moving in the opposite direction. Thank you.